Hello, everyone, and welcome to part 2 of derivatives of inverse trigonometric functions. This section actually includes a little bit about inverse functions in general, not just inverse trigonometric functions, starting with this very tiny little theorem that says if f is differentiable at every point on the interval I, so two things it's going to be if one, it's differentiable at every point, and two, the derivative is never zero, then the function has an inverse, and the inverse is differentiable at every point on the interval f1. So you don't have any room. It goes to the exploration next, but I'm actually going to do a problem for you first because I don't want you to be busy writing anything down. This is a little bit of a tricky concept, and so I just want you to watch. So I'm going to go ahead and make a graph, and I'm going to graph something that we all know well, and that is y is equal to x squared. So x squared is 0, 0, 1, 1, 2, 4. It's on the other side as well. Now you may remember that the way we decided in pre-calculus whether or not something had an inverse function was whether or not it passed the horizontal line test. This does not pass the horizontal line test. So now we're learning a new way to know if something has an inverse, which is step 1 has to be differentiable at every point. It is. But the derivative is never zero, which it's not. So I'm going to limit the domain. When I limit the domain to x is greater than or equal to 0, now it is differentiable at every point, and the derivative, can't ever be equal to 0. Hold on. Get my little eraser back. Just greater than 0. Okay. So the inverse function is y is equal to the square root of x. So that starts at 0, 0, 1, 1, 4, 2. Looks like that. Remember, inverse functions are reflective over the line y is equal to x. Now, here's the interesting fact that I want to teach you. The point 4, 2 is on this one. The point 2, 4 is on this one. Let's look at their slopes. The slope of the blue one, the square root one, is 1/2 x to the negative 1/2, or 1 over 2 square roots of x. That means that the slope at 4 is equal to 1 over 2 times the square root of 4, which is 1/4. The derivative of the parabola is 2x, which means that the derivative at 2, so I consider these 2 points to be the ones that match up, even though I'm not calling it 4, I'm doing the derivative at 2, is equal to 4. Do you see a relationship between these two? They're reciprocals of each other. So here's the weird rule. Again, you don't have to write anything down yet. It's all going to be in your notes. Here's the weird rule that I want you to know. If you have a function that has on it the point AB, and if you have an inverse function, remember it has a little -1. It's not a prime, it's an F inverse. That has the point BA, then the derivative of the original function at A is equal to 1 over, not -1 over, they're not perpendicular, 1 over the derivative of the inverse function, but at B. So the x and the y switch. And if you look at that, see, this is really shallow, and this is really steep. As this gets more steep, this gets more shallow. See how that works? So this is a little tiny topic. You can see I gave it like not even a whole page. And yet 1 year, they chose to make this one of the 6 AP open-ended questions. They took this tiny, tiny little topic and they made it into 1/6 of the open-ended question, which was huge. The average score in America, by the way, these are graded on a score of 1 to 9, each question. The average score in the United States of America on this question was a 0.9 out of 9. In other words, everybody bombed it. So it just shows that any little topic could be on there. We have to know everything. But now we'll do an example that's actually in your notes. You can screenshot this if you want to, but we're going to do one now that's in your notes so that you can do it yourself. All right. Let f of x be equal to x cubed plus 1. So let's obviously start by graphing it. 1, 2, 3, 4, 5. 2, 3. So normally I would do 0, 0, 1, 1, negative 1, but I'm going to move it up. And then it would be 2, 8, which is really 2, 9. And then 2, 1, 2, 3, 4, 5, 6, 7. I can actually reach that one. So it looks something like that. That's the regular function. The inverse function is, now look what it's saying. It says, can I find the derivative of the inverse function at 2 without knowing the formula? So this is one that you could find by hand, but they're going to give you one that's so hard you can't find it by hand. So we're going to practice doing it without actually finding the inverse function. So if you want to know the inverse function derivative at 2, it is going to be the reciprocal of the regular function at what point? Remember, they switch. So this one must have the point 2 comma something, and the inverse function must have the point, or did I say 2 comma something? 0 something something comma 2, and this one has 2 comma something. So what would create this to be a 2? A 1. 1 cubed plus 1 is 2. So this must have the point 2, 1. So what is the derivative of this function, 3x squared, and what is the derivative at 1? It's 3. So since the derivative of this at 1 is 3, then the derivative of the inverse function at 2 is 1/3. And that's the way that works. It's a little tricky. Let's actually do it the long way now, finding the inverse function. So we just found the derivative at 1, and then we found it to be 3. The inverse function would have, so 0, 1, 1, 0, 0, or negative 1, 0, 0, negative 1, 1, 2, 2, 1. So it's going to go something like this. So it makes sense that this is 3 and this is only 1/3. As this gets steeper, this gets more shallow. They're still both positive slopes. It's not perpendicular. It's not negative reciprocal. Look how steep that's getting and look how flat that's getting. Okay? So if you can find the inverse, that's great. But they're purposely going to give you one where you got no shot at finding the inverse. So you have to know this little teeny tiny rule. The conclusion is, if there is a tangent line to the graph at the point a comma f of a, then that line will reflect across y is equal to x to become the tangent line to the graph of f inverse at f of a. All they did was switch the points. And the slope of the reflected tangent line will be the reciprocal of the original tangent line. So here's the fancy way of saying everything that I just explained. Okay, so we're actually going to do a problem now with an inverse trig function. So let f of x be equal to cosine of x plus 3x. So there's two parts to this. One is we have to say that f is differentiable. We actually haven't done a lot of this yet. This is going to be in a couple lessons from now. But pretty much something's differentiable if it doesn't have anything sharp or pointy. So an absolute value has a point where it's not differentiable. This is called a cusp, not differentiable. But if the parts are differentiable, then the whole thing is. Cosine is nice and smooth. And of course, 3x doesn't have anything pointy in it, even when you add them together. So we'll talk more about that later, but you can take my word for it now it is. The second thing it says at the top of your paper is that the derivative is never 0. So I take the derivative and I get negative sine of x plus 3, which if you guys think about this, negative sine of x plus 3. So now I'm up there, and it's going to go up to 1, down to negative 1, up to 1, down to negative 1. Is that ever going to be equal to 0? Definitely not, okay? It never even comes close to the axis. So the derivative is never equal to 0. Part B, find f of 0 is cosine of 0 plus 3 times 0, which is 1 plus 0 is 1. That means that the point 0, 1 is on f of x. The derivative of 0 is negative sine of 0 plus 3, which is sine of 0 is 0 plus 3. So the derivative at 0 is 3. So their question is, what is f inverse at 1? That's saying if this is the x-coordinate, what's the y-coordinate? Well, since this is an example of one that you would never be able to find this inverse. But since the regular function is 0, 1, this one must be 1, 0. So f inverse of 1 is 0. And now it's asking you for what is the inverse derivative at 1. The inverse derivative, lots of parentheses now, at 1 is going to be 1 over the regular function, the original function's derivative at 0. It's always going to be the reverse point. So this is what I'm trying to find. F inverse derivative at 1 is 1 over, and do you remember we found this? F prime of 0 is 3. So there you go. Now, I walked you all the way through this. This question, if it had just started with, here's the function, find this, you would have had to be thinking all these steps through. So we found f of 0. We found f prime of 0. Then we thought about what that means that f inverse of 1 is. And that's what allowed us to do f inverse derivative at 1. So 4 or 5 steps happened there between the original question or the original statement and the question. You're going to be able to have to do those steps on your own. Okay, another super interesting problem. Graph f of x is equal to inverse sine of sine of x. So I would love to think that you're getting your graphing calculators out, making this window, x goes from negative 2 pi to 2 pi, but I know you're just going to wait for me to graph it. So you can put zeros at 2 pi, at 0, at pi, and at 2 pi. And what that ends up doing to it is it makes it go up to there, and then down to there. This is what it looks like. There. Okay, so it's about 1.5 that it's going to go up to. And it is just like an absolute value graph. Very pointy. There we go. So if you've done it on your graphing calculator, I know you didn't. All right, so what is the domain? Domain means what can x be? X can be anything. This graph is uninterrupted, it is continuous. What is the range? So this specifically isn't just 1.57. Isn't just 1.5, it's 1.57, which hopefully you recognize as pi halves. So it goes from negative pi halves up to pi halves. And if you think about that, that is the range for inverse sine. Remember how we said that if you have an inverse function and it's positive, you would give the answer in quadrant 1. And if it was negative, you'd give the answer in quadrant 2. I know all this trig is coming back to you. So we always have given the answer. So just for example, if you had inverse sine of 1/2, you'd say, oh, that's pi 6. But if I asked you for inverse sine of negative 1/2, hopefully you would have said negative pi 6, not 5 pi 6. We always gave the answer in quadrants 1 or 4. So the range goes from negative pi halves to pi halves. But just by looking at your calculator, you might not have, your calculator's not labeled that way. You've been like, oh, it looks like it's about 1.5. It is. Pi halves is 1.57. Okay, at which points is f of x not differentiable? It is not differentiable at pi halves, at 3 pi halves, at negative pi halves, and at negative 3 pi halves. That is the set of numbers where it is not differentiable. Could you have said it differently? You could have said x is equal to k pi halves, where k is odd. And that would have been okay too, if you thought of that. But since it was a restricted window, I decided it was also a pretty limited number of things I could do. All right, here's the fun part. So I did copy the graph from my calculator. I'm going to make a sketch of y is equal to f prime. You really should pause this and see if you can do it. Can you make a graph of the derivative? Okay, I'm going to do it for you now. So through this whole thing, the slope is 1. So my derivative graph I'm going to make in blue. Right here, the slope is 1 the whole entire time. And then I'm going to put an open circle because at that moment, there's no derivative because it's pointy. And then for this whole section, the slope is -1. So from here all the way over to here, the slope is -1. And now through this whole section, the slope is 1. It's cool, right? And then from pi halves all the way over to 3 pi halves, the slope is -1. So if you do this on your graphing calculator, then it'll overlap them and it'll look just like this, which is really cool. Okay? All right. Now it says we want to find it algebraically. So the original function is inverse sine of x. Oh, sorry. Inverse sine of x. So this is my u. So the formula for the derivative of inverse sine, can you hear my papers moving? I'll look it up, make sure I get it exactly right, is 1 over the square root of 1 minus sine squared x times the derivative of u, which is cosine of x. Okay? Then this becomes cosine of x over the square root of cosine squared x. There's all that trig coming back. The square root of something squared almost goes back to itself, but it always makes it positive. Think about that. If you have 3 squared and you take the square root, you're going to just get 3 again. But if you have negative 3 squared and then you take the square root of 9 is going to be 3. So the square root of x squared is actually the absolute value of x, not just x. So what does this give you? Graphically, that's why it gave us 1 and then negative 1. Because cosine divided by cosine, when cosine is positive, will be 1. And when cosine is negative, it'll be negative 1. And that's why the graph kept switching from 1 to negative 1, from 1 to negative 1. Kind of cool, right? All right, last one. A particle moves along a line so that its position at any time t is given by x is equal to arctan. I have no idea why it came out in such weird writing. Arctan t. It's like a totally different font and size and everything. Prove that the particle is always moving to the right. So in order for something to be moving to the right, that means its velocity is positive. Remember, up and right are both positive. Down and left are considered negative. So pretty much they just want to know if the velocity is positive. So velocity is equal to the derivative of x with respect to t. This is a t equation. So the derivative is going to be 1 over 1 plus t squared. And no matter what t is, that's always going to be positive. 1 over 1 plus t squared is always positive. Prove that the particle is always decelerating. So now I need the next derivative. So I'm taking the derivative of the velocity. I'm actually not doing an inverse trig function anymore. This is just straight up quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared is negative 2t over 1 plus t squared squared. So since this is always going to be positive, and the top, since t is greater than or equal to 0, this is always negative. And a negative divided by a positive is going to be negative overall. Quick little side note here. Another way to do the derivative would be to switch this to 1 plus t squared to the negative 1. Whenever the top is a constant, I tend to do it this way. But I just like to keep showing you both ways because I don't know if it's any faster or not, but that's how I usually do it. Okay, last part. What is the limiting position? When you see this, you need to be thinking, what is the limit as x, or in this case t, approaches infinity of, I guess they called it x, not s, yeah, x, which I'm actually going to put the formula in there. Arc tan of t as t goes to infinity. How are you going to figure that out? So way number 1 is to plug infinity in, which obviously you can't do. Way number 2 is to simplify algebraically, which you're not going to do. And way number 3 is to make a graph. So you are going to have to be familiar with the inverse function graphs. But if you think about it, tangent looks like this, right? That's actually one inverse graph that you probably know pretty well. And remember, the domain and the range switch. So on the original graph, of tangent of x that goes like this. The asymptotes are at pi halves and at negative pi halves. So now everything is switched. Now this is pi halves and this is negative pi halves. And because I've already said it once today, if you had been given inverse tangent of 1, you would have said pi fourths. But if I had asked you for inverse tangent of negative 1, you would have said negative pi fourths. You wouldn't have given me a quadrant 2 answer. Tangent goes in quadrants 1 or 4. In other words, it goes from negative pi halves to pi halves. That's what my graph looks like, negative pi halves to pi halves. So as t goes out to infinity, what is this graph slowly becoming? Pi halves. So if you're thinking, this is really hard. Yeah, this is so hard. This involves everything you learned in pre-calculus. Now we're bringing limits back. It's just a lot to know. But you guys are also really smart. And you can do this. And we're going to keep circling things back and bringing it back up. And by the end, you'll know it really well. So no worries. All right, that's it. Have a great day.